Direct Comparative Framework between VMT and TDA Models, number 1411, VMT Sharp 739, TDA Sharp 022, October 30, 2025. Gerald C. EclaireMD Foundation. Category, Methodology. Introduction. In my 1,410 medical research papers, more than half, about 760 studies, have applied both physics-based energy models and mathematics-based geometric models. These two methods are independent yet highly complementary in explaining the pathophysiological behaviors of complex medical systems. The Viscoplastic Medicine Theory, VMT, translates biological dynamics into energy-based equations derived from physics, material science, and mechanical engineering, while Topological Data Analysis, TDA, converts multidimensional health data into geometric areas, volumes, and structural patterns of data point connectivities. Both aim to quantify system stability, detect transitions or turning points, and identify key influencing factors. By applying these two frameworks to the same medical dataset, I can verify consistency and differences in data patterns, and predictive outcomes across different scientific domains. My findings show that both models consistently yield similar results and patterns, confirming that physical energy and geometric topology describe the same underlying biomedical reality from two distinct, but complementary scientific perspectives. Outlines. 1. Research goal. Example cases. First example, studying stroke risk resulting from obesity, diabetes, and hypertension. Second example, evaluating cancer risk, arising from genetic, environmental, and metabolic factors. Many additional examples can be found throughout my medical research work. VMT model. Define the clinical question and select one measurable output strain, for example, stroke risk severity, and 3 selected stressors: obesity, glucose, and blood pressure. The analysis is conducted through the levels of viscoplastic energy intensity, generated by the interactions between a single strain and multiple stressors. TDA model. Use the same clinical question and dataset, but define the geometric stability objective, for example, the contraction of clusters, simplification of shape, or reduction in geometric complexity. 2. Data window. Choose a consistent time scale such as days, weeks, months, quarters, or years, and keep it identical for both models. VMT. Specify exact study periods, for example, 2018, 2021, 2025, and the sampling cadence. TDA. Use the same periods and cadence to ensure a direct comparison. 3. Variables. Use the same single output strain or disease symptom, with up to 5 input stressors or influential factors for data simplicity and computational efficiency. VMT. Select one strain metric and a few stressors. Fewer than 5 if possible. Name each variable clearly with its unit. TDA. Use the same variables as coordinates for each data point in the point cloud, adding a label for each time period. 4. Normalization. Apply identical normalization factors, usually healthy levels or generally accepted reference levels. For both models, VMT, define anchors and scaling factors. Example anchors, pages 45 mm of mercury, MAP 84 mm of mercury, glucose 129 mg per deciliter, BMI 25, sleep 7.9 hours, walking steps 7,000 for post-stroke condition, or 10,000 for normal condition, depending on situations. These represent healthy reference levels. TDA, apply the same scaling to every coordinate before constructing the point cloud. 5. Data preprocessing. Ensure the dataset is clean, consistent, and ready for both analyses. VMT, review and remove abnormal or impossible data points when necessary, but keep physiologically realistic disease outliers. When they provide meaningful insight, align timestamps so that all variables correspond to the same date or period. If the dataset is large, average daily data into weekly, monthly, quarterly, or even annual intervals to create smoother and more comparable trends. TDA, use the same cleaned and time-aligned dataset and apply identical aggregation rules before computing topological structures. Notes to maintain consistency. A. Use the same dates, variable names, and units in both models. B. Keep your post-stroke anchors, pages 45, MAP 84, sleep 7.9 hours, steps 4,500, unless intentionally changed. C. Round values to whole numbers for steps, 1 decimal for hours, and 1 decimal for mmHg when needed. 6. VMT model construction. 6.1 Compute the output strain change rate over time, det. Subtract the strain value of time point 1 from that of time point 2. Then divide by 1, since the time interval between points is constant. Repeat across all consecutive time points to cover the entire study period. 6.2 Calculate the stress value at each time point. Multiply each input stressor's value by the strain change rate. Det. of the same time point, stress value, input value, times, strain change rate of time. This gives the instantaneous stress level for that specific variable. 6.3 Draw the strain stress curve. Plot strain values on the x-axis and stress values on the y-axis. Connect the data points to form the 2D strain stress curve for each input stressor. 6.4 Calculate the area under the strain stress curve. The area underneath a curve is calculated using integral calculus. Using this concept, sum the stress values, curve heights, multiplied by the time intervals. Delta t is 1, to approximate the area under the curve. This area represents the VMT energy generated by each input stressor. 6.5 Compute total and relative VMT energy over the entire time period. Add the VMT energy of all stressors to obtain the total VMT energy at each time point. Then sum across all time points for the cumulative VMT energy. Next, divide each stressor's VMT energy by the total energy to get its contribution ratio, percent. VMT energy contribution percent. Each stressor's VMT energy, divided by total VMT. Compare and rank these ratios to identify which input stressor contributed most to the total VMT energy. 6.6 Construct the cumulative VMT energy curve. List total VMT energy at each time point and add them sequentially to form the cumulative VMT energy percentage curve. This curve shows how energy accumulates over time and reveals the turning point, where the health condition begins improving. Decreasing energy, or worsening, increasing energy. 7. TDA model construction. 7.1 Compute data transition rate between consecutive time points. Similar to VMT's strain change rate, DET, TDA, calculate the change of each variable, strain or stressor, between two consecutive time points. This describes the temporal movement of each data point in geometric space. 7.2 Construct the point cloud for each time point. At every time point, plot all variables, same as those used in VMT, as coordinates in multidimensional space. Each point represents the biomedical state of that period. 7.3 Build the topological structure. Compute pairwise distances among all points to capture their spatial relationships. Apply the Vietoris-Rips filtration method, linking nearby points, step by step to reveal the hidden shape of the data. To connect points within defined distance thresholds. This process exposes topological features such as connected components, B0, loops, B1, and voids, B2, which describe the system structure, stability, and complexity, analogous to the strain stress curve in VMT. 7.4 Quantify geometric shape characteristics and total persistence. Before calculating total persistence, derive the eigenvalues and eigenvectors from the distance or covariance matrix of the point cloud. The eigenvalues represent the principal magnitudes of geometric variation, while the eigenvectors define the dominant directions of deformation or contraction within the data manifold. Together, these algebraic indicators provide an analytical bridge between TDA, geometry and VMT energy, linking geometric stability to physical energy orientation and intensity. The total persistence, the sum of the lifetimes of all topological features, serves as the geometric equivalent of total VMT energy. High persistence indicates a larger and more irregular shape, such as a multi-angled polygon, representing instability. In contrast, low persistence corresponds to a smaller, smoother, and more compact form, such as a tight, small sphere or ball. The geometric equivalent of lower energy in VMT. 7.5 Compute contribution ratios and relative impacts. As VMT calculates each stressor's energy contribution, TDA identifies geometric influence by measuring how each variable alters data point distances and deforms the overall shape, area, or volume. The variable that causes the greatest deformation contributes most to system instability. The topological counterpart of the highest VMT energy contributor. These deformation effects can also be traced through the eigenvalue-eigenvector results obtained in the previous step. Larger eigenvalues correspond to variables that drive stronger geometric distortions or expansions, while their associated eigenvectors indicate the principal directions of such changes. Therefore, both the VMT energy contribution ratios and eigenanalyses together quantify how individual variables shape overall system stability, directly linking TDA's geometric interpretation with VMT's energetic framework. 7.6 Construct the cumulative shape contraction curve. Analogous to the cumulative VMT energy curve, calculate the reduction of geometric area, 2D, volume, 3D, or total persistence across time. Plot these values sequentially to observe geometric contraction, health improvement, or geometric expansion, health deterioration. A continuous contraction indicates recovery and stability, while expansion reflects rising instability. Summary of conceptual parallelism. VMT tracks energy changes through stress-strain interaction dynamics, while TDA tracks shape, area, volume, and distance changes through geometric contraction. Both measure system stability. VMT quantifies it in the energy domain. TDA quantifies it in the geometric domain. Their outputs often converge because both frameworks describe the same biomedical reality, through two complementary scientific languages. Energy in physics and geometry in mathematics. Scientific significance of dual model validation. When two mathematically independent systems, one based on viscoplastic energy, VMT, and the other on topological geometry, TDA, produce similar patterns and identify the same turning points, it reinforces the validity and reproducibility of the research findings. Such agreement shows that the observed biomedical behaviors are not artifacts of a single analytical method, but represent genuine pathophysiological phenomena grounded in real biomedical data. This cross-validation between physics-based energy variations and mathematics-based geometric variations confirms that biomedical stability, recovery, and deterioration can be consistently interpreted through both energy and shape, forming a unified understanding of systemic disease conditions and overall health dynamics. Conclusion: this dual methodological illustration paper is not only academic but also necessary, meaningful, and scientifically valuable because it unites two powerful yet independent frameworks: physics-based VMT energy and mathematics-based TDA geometry, to describe the same biomedical reality, by demonstrating that viscoplastic energy and topological contraction yield consistent results. It establishes a clear and reproducible bridge connecting physics, mathematics, and medicine. This dual model validation strengthens scientific credibility and introduces a practical, quantitative method for understanding disease mechanisms and system stability with greater precision and clarity. I am confident that my combined research approach using both VMT and TDA, where physical and mathematical results align with pathophysiological conclusions, is unique, and at this time, I may be the only author in the world applying this integrated methodology on medical research work. The idea that energy and geometry tell the same biomedical story is profound, as it captures the essence of how nature operates through different, yet consistent scientific languages. Medicine is no exception. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.